Hello, welcome to this presentation, Application Processor Security. The topic of this presentation is Foundational Security Enablers. Before we move along too far, let's define security. Security at its core is protecting assets that have value from threats, whether that threat be stealing the value of that asset or taking control of it in such a way that it's not used for what it was supposed to be used for. As you do a threat analysis, you're going to determine exposure points, where the most likely places for assets to be at risk, whether that be how they're being stored or how they're being utilized at runtime or how they're being transferred from maybe one device to another. These exposure points are going to be the focus of your security enablers. These enablers are going to help you protect those assets from threats based on the exposure points that you deem, based on your system and the use of it, as the most at risk. TI Security Enablers is really a toolbox of different options and capabilities that allow you to protect the assets that you've chosen to protect against the exposure points that you deem valuable in your system. The rest of this presentation will cover how to understand and utilize these security enablers. These enablers can often be viewed as a pyramid structure where you're going to build at the base and work your way up, depending again on that threat analysis and how you're trying to protect different assets in your system. The topic of this presentation is really the foundation of that pyramid, or the foundations of security, as the title suggests. We'll take a look at each one of these that are included in the foundations for security, starting with one that is really the cornerstone, which is called Secure Boot. Secure Boot is really making sure that your system is going to run code that it was designed to run, and make sure that it can't run other code that someone might try to inject in the system. Really guaranteeing the integrity of the system from a software and a hardware perspective, and establishing root of trust for the rest of the software that's going to run on the system. Device identity and keys is used to make sure that a device that's talking on a network is a known device. It's not a rogue device, or it's not a device that's running software that it's not supposed to be running and trying to communicate bad information or misinformation to the rest of the system. Crypto acceleration is really one of the hallmarks of enabling security. It's going to be used not only in Secure Boot, but in encrypting data as it's sent around the system. And accelerators are necessary for this, particularly in the early boot phases when high-powered processors aren't available to do the cryptographic operations. So acceleration is going to help some of the rest of the boot process, as well as just make it easier for the system. And it guarantees more security, since these hardware implemented accelerators are inherently more secure than a software accelerator, for example. The last one is debug security, and this is just locking down the JTAG port, or the debug port, that were used to design the system, and necessary a lot of times for design and development, but not something you might want someone having access to in a production system. So we'll see how the debug security allows you to disable that. We'll take a look at each one of these in a lot more detail as we go through the presentation. But before we get too far, we need to understand that each one of these basic architectural elements need to be baked into the architecture of the system, or the SoC architecture being used to build the system. Security really needs to be a foundational element of the aspect of the architecture in order to make sure that it is truly secure. You can't really bolt security onto something and make it as effective as something that's built in to the system. And that's exactly the case for the TI AM6X security architecture. It is one of the core components of the overall architecture of the AM6X device family. And as you can see, it's joined with a lot of other basic components, like a compute architecture with something to a quad-core Cortex-A53, or even larger processing cores, and a number of them. Graphics and display capability, for example, for HMI applications. Audio, video, and analytics for other signal processing applications. All of this paired with power efficiency, so that all of this can be done on an efficient power budget. Paired with real-time cores a lot of times to enable real-time capability in embedded systems. And paired with a lot of connectivity in order to allow these chips to interface with the rest of the system, whether it be basic connectivity like SPI or I2C or UARTs, all the way up to things like USB, PCIe, and extensive networking capability, including TSN, or time-sensitive networking. All of this pairs together to form an architecture that can build a number of flexible and capable embedded systems with security inherently at the core. The security controller is the heart of the security architecture on AM6X. This is really a separate security island needed for security processing that can't interact with or is very protected from interaction from the rest of the system. The security controller oftentimes includes a processor. Oftentimes this is up to a dual-core Cortex-M processor with secure ROM and secure RAM, and other peripherals like timers and watchdogs, and capabilities like security control keys and one-time programmable capabilities to store keys and hashes as necessary to implement things like secure boot. The controller itself is paired with the cryptographic subsystem that we mentioned earlier to enhance and speed cryptography operations, and then also with a secure DMA and interprocessor communication, or IPC, that allows the efficient movement of data amongst these systems to implement security. All of this is wrapped with firewalls to protect the security controller and the different aspects of it from the rest of the system. As we mentioned earlier, this is kind of an island set apart within the chip, but in order to do security operations. For example, you don't want a Linux process running on your Cortex-A processors to be able to come in and read your one-time programmable keys or hashes that your security is all based upon. You want that to be well protected, and the security controller and the firewalls that protect it are going to help implement that security, keeping that Linux application from being able to read things that it should not be able to read. As you can see, the security controller really is the core component of the overall security system and baked right into the architecture. It's one of the first things that's going to run at boot, for example. All right, so we come back to our foundational enablers, and we can now see how to use the architecture that we quickly reviewed and see how that it implements each one of these important security enablers. Let's start with Secure Boot. Secure Boot is very important for an embedded system. It's really the way that we make sure that the software that's being paired with the hardware in an embedded system are the proper match. As we can see on the right-hand side of the screen, in a non-secure system, really the system is going to run any code that is placed in flash at the right address for when the processor starts up. And this is great for design and development, but obviously for a system that has risks and needs to implement security, this is not going to be good, because anyone that knows how to put code into that flash at that address is going to be able to get the system to run code that it might want to get them to run. And that's a non-secure system. For Secure Boot, we're going to pair a key that's going to be stored inside the device with a lock, if you will, with signed code. So we're going to use asymmetric encryption to pair the code that's going to run with the key that's stored in the device, so that when the device boots, if the key doesn't unlock the code, or if it can't handle the signing process, then the device won't boot, thus implementing Secure Boot. And this allows you to start executing security code and really establish your root of trust and maintain a chain of trust all the way up through the upper layers of software that the system is going to run. Really the foundation for security in a modern day embedded system. This helps take care of takeover protection. It maintains the integrity of the system. You know that your device or your system is only going to run code that you've authenticated and allowed it to run. And you can also do IP protection by encrypting the code as a separate process, and that allows you to maintain confidentiality as well. You can't just take the code out of the device because it will be encrypted. So these are a couple of the elements of Secure Boot: getting the device up and running in a secure manner, pairing it with software that the designers have signed off on, quite literally, allowing it to run only code that has been signed properly. And that's the basics of Secure Boot. These secure devices, once you turn on security, are security enforced devices. These are really designed for production type systems. They enforce Secure Boot, as we just saw. JTAG, or the debug port, is also closed. And all the other security features that we'll review as security enablers will also be turned on and enforced. So this device has security enforced. That's the high secure security enforced nomenclature. But we also provide a device that doesn't have security turned on, and this is really for development and testing, and this is called high security field securable. That's what the FS stands for. So field securable devices do not implement secure boot. You don't have to have your code signing and all of that in place. You can just get code into Flash and start doing quick development. JTAG is open, so you can do debug except for the security controller, and security is largely disabled on these devices. So that you can do design and development and move through your development process as fast as possible, and then enable security when you're ready. And you do that with a non-reversible, one-time programmable writing process with tools provided by TI. And that would allow you to convert an FS device, a field securable device, to a security enforced device at whatever point in the production cycle you'd like to. And that allows you to have non-secure devices for development and testing as needed, but move to security before you move to production and release the devices to the market. These are both in contrast to general purpose devices. We do have GP devices for some product families still. These are devices that cannot have security on them. They're not designed for security at all. You cannot turn security on, and thus should only be used in systems where you know security will never be needed. And that's becoming pretty rare these days, so we highly recommend people start with HSFS devices, field securable devices, and then turn on security when they're ready in their production cycle. All right, so that covers secure boot, and now we can look at our other foundational enablers, and we'll start with device identity and keys. Device identity is all about being able to communicate in a secure manner with other devices in a network or in a system. So as we can see in the diagram, the device wants to communicate with something in the cloud, and the cloud can do a challenge response type system to say, hey, who are you? Are you allowed to be communicating on this network, to make sure to protect the network from bad actors or devices that are trying to do things they're not supposed to? So this is all based on hardware unique identification, another basic security enabler that we have in TI devices, and this is great for network authentication. On the flip side, it's also great for detecting unauthorized accesses. So if you have a device that's trying to connect to you, maybe somehow they've broken through some of your security layers and they've been able to hack a system and make it look like one of your devices, but its unique ID is not in the approved database, and now you're going to know that somebody is trying to get into your system with a bad device as well. And you can also implement other security features at the system level to take advantage of that. Unique IDs are also great for fleet management. A lot of times these days you need to be able to say that a given system is got a certain flavor of software on it, a certain versioning, a certain package, so that if that package comes up with a warning or a critical bug in it that may be a risk to security, you can quickly identify the systems that are running that software and deploy a patch as necessary to fix that, or at least know what systems are vulnerable to that problem. So unique identity is a very important aspect of security enablement, and it's very good for networks and other systems. The next one is cryptographic acceleration. Kind of mentioned this earlier. We have a cryptographic accelerator paired with the security controller as part of the security subsystem. And what this does is it simply accelerate cryptographic operations. This is particularly important for secure boot when you're using some of the smaller, less capable cores in the device, and these cores aren't as good at some of these large cryptographic algorithms. So a cryptographic accelerator is going to simply accelerate those, make them faster to speed up boot and enhance security. These cryptographic subsystems also have the capability to very intelligently know whether data is coming from the security controller or through the secure side of the system versus the non-secure side of the system, and keep that data separate so that it doesn't get polluted. And you can see that the security subsystem, the cryptographic subsystem is going to support a number of the popular cryptographic standards today, like asymmetric, symmetric hashing, and random number generation, which are so important for the basis of security today. Here's a quick summary of the common cryptographic operations that are supported on TI processors. JTAG debug security is our last security enabler. This is simply being able to turn off the debug port or protect it so that not anyone can just get access to it. If you're familiar with JTAG, you know that JTAG is a very powerful way to get into a system, particularly during development, and see what's going on in that system, with all the way from peeking and poking memory to seeing what process is running, and so on and so forth. So obviously you don't want a bad actor to be able to have that level of visibility into a secure system. So disabling security or protecting it as necessary is a very much important part of the security enablement. And TI devices support this as well. Essentially, when you connect to a secure device, you're going to have to go through a challenge response mechanism to prove that you should have access to the JTAG port, and of course the JTAG port can be permanently disabled as well if that is required. All right, that covers the rest of our security enablers and really finishes up our talk on foundations for security. These are really the very important aspects of security enablement, really starting with Secure Boot as one of the foundational elements to a modern day security system for embedded systems. Here is a quick review of the security features that we've discussed so far. We started with the security controller, as that is a basic element of the security architecture. It includes the processor, the cryptographic subsystem, as well as DMAs and interprocessor communication to help move data around the system. And it's all protected by firewalls from the rest of the system. Our field securable devices are what you want to start with if you're going to be doing a secure system or you think you may need security in the future. These devices behave as unsecure devices until you turn on security, and then they become secure, and that helps you do your design and development without security enabled, and then as you see the need, you can move to a secure architecture when your design calls for it. Secure Boot is one of the basic elements of this security, and it's going to make sure that the processor is going to be running only code that has been authenticated for that system, and it also can be used with encryption to make sure that the code is protected while sitting in on-chip, off-chip flash if necessary. And the Secure Boot methodology implemented on TI processors is based on the industry standard X509 based booting certificates. We have a dual root key support, which means if your primary key were to be compromised and you need to switch that, then you can switch to a backup key and move the system over to that to protect that, continue to protect that system if a key were compromised. All of this is implemented based on the firewall architecture, which will protect the security system from the rest of the system and maintain that your secrets and everything that's being processed by the security system is only accessible by those who have appropriate access. The smart cryptographic subsystem is very important for accelerating all the different encryption, decryption, hashing algorithms that are needed in order to implement modern day security, and it's going to improve your boot time and make sure that you're not, the algorithms aren't hacked as they're implemented in hardware. And lastly, of course, we talked about the debug control. You can debug in a secured system if you configure things properly, and you can disable debug, obviously, for those that don't need to have access to it. All of these capabilities are available to you with the AM6X processor family. It's all included in the basic offering. You don't have to worry about am I looking at a secure processor? Am I not looking at a secure processor? All the basic components are included in the standard TI offering, which really allows you to start your design and then turn on security when you're ready and when is necessary for your process or your projects. Everything from the EVM you buy, the software that you're going to use, the devices that you're going to sample. If you choose to use the field securable devices, you're going to be able to go through the design process using that one flow, and then as was indicated, you can just turn on security when needed. If you'd like to get started with security or give it a try, we have a security academy that's going to walk you through in a step-by-step manner how to implement secure boot and use the JTAG debug control on a TI EVM. And what this allows you to do, if you've never done this before, is just go through the process and see how it works. Increase your confidence, increase your learning, and you can see how you can verify secure boot, how you can unlock JTAG for debug of secure systems, and really get a very good start with enabling security in your embedded systems. And there are links provided here for different family members of the TI processor family. I want to thank you for joining this presentation today. I hope you felt it's been valuable. These are just a few of the security enablers that serve as the foundation for a modern day security system in an embedded system. Hope you have a great rest of your day. Thank you very much.